So we know that unstable nuclei will decay into nuclei that are stable. What we have found is that some nuclei decay at different rates than others. We use the term half-life to describe how long it takes for half of a sample to decay. Radioactive decay reduces the number of unstable nuclei by half over a certain amount of time, and this is called the half-life. So if we start with a nice round number, like 1 million atoms, after one half-life, the number of unstable nuclei will be 500,000. After a second half-life, that 500,000 will be reduced to 250,000. After a third half-life, 125,000, and so on and so on. This exponential decay can be represented in what we call a decay curve, and this is just how the number of unstable nuclei decrease as a function of time. Not all nuclides have the same half-life. The most unstable have a half-life of 10 to the negative 23rd seconds, while some have a half-life of more than 10 to the 16th years, so it's quite a range. However, all decays fit in a specific pattern that we can express as an equation for the decay of a specific nuclide. The number of nuclides left as a function of time is equal to the number of nuclides at the beginning times the exponential to the negative lambda t. T is the time the sample has spent decaying in seconds, and lambda is the decay constant. This constant is specific to the type of nucleus, and the larger the decay constant, the shorter the half-life. We can derive the half-life of a particular element using this decay equation. At one half-life, there are 1/2 the original parent nuclei left. So n actually equals 1/2 of n naught. T in the original equation becomes the time of the half-life, so we can specifically refer to it as t 1/2. Now, in order to determine t 1/2, we need to get it out of that exponent. Luckily, that's just a little bit of algebra, because first off, the n naughts will cancel out on both sides. To get rid of that exponential, we need to take the natural log of both sides. Natural log times the exponential is 1, so that gives us the natural log of 1/2 equal to the negative lambda times the half-life. Now the natural log of 1/2 is equal to the natural log of 1 minus the natural log of 2. This is nice because the natural log of 1 is actually 0, and this lets us simplify down a bit to the natural log of 2 equal to the decay constant times the half-life. Half-life then is equal to the natural log of 2 divided by the decay constant. Of course, natural log of 2 is a constant itself, so we can work that out and write it as 0.693 over lambda is equal to the half-life. So this equation gives us a little better idea of how fast a sample will decay. If lambda is big, then the half-life will be small. If we know the half-life of a particular isotope, we can use the decay equation to determine how long the sample has been decaying. So in any given sample of material that contains a radioactive substance, we can compare the amount of parent atoms to the amount of daughter atoms. The ratio that is found allows us to determine the age of this sample. This is what is referred to as radioactive dating. Carbon-14 dating is probably the most known example of this. Carbon-14 has a half-life of 5,730 years, and it has the same chemistry as stable carbon, so it will mix in and become a part of every living organism. What we find is that the ratio of carbon-12 to carbon-14 in any given sample of living tissue is the same at 1.3 trillion particles to 1. This means that in a living organism, there is one carbon-14 particle for every 1.3 trillion carbon particles. When the organism dies, carbon-14 is no longer being added to the organism. So whatever amount of carbon-14 is present in the tissue at the time of death becomes the number of parent atoms and undergoes beta decay to become nitrogen-14. At any given time, then, we can compare the amount of carbon-14 to the amount of other living tissue to determine how long the carbon-14 has been decaying, and thereby determine the time at which the organism died. A famous case of carbon dating involves the Shroud of Turin. The Shroud of Turin is a piece of cloth that has a bloody body image imprinted on it. In 1354, it turned up and was declared to be the burial cloth of Jesus Christ. There has always been some skepticism surrounding the shroud, and in 1988, permission was given for 3 independent labs to perform carbon-14 dating. The amount of carbon-14 was found to be 92% of that in living tissue. So 8% of the original amount of carbon-14 had decayed. Knowing that and our decay constant for carbon-14, we can use our decay equation to determine when the blood was placed on the cloth. Since we know the ratio of parent atoms to daughter atoms, we can rearrange our equation to reflect that. And we can get rid of that pesky e by taking the natural log of both sides. The natural log of 0.92 is negative 0.0834. And we can rearrange to solve for time. Now we also know that the half-life of a substance is equal to the natural log of 2 divided by the decay constant. And we know the half-life of carbon-14 is 5,730 years. If we solve for the decay constant here, we can plug that expression down into our time equation down here at the bottom. So we have kind of a fraction nightmare going on there, but if we solve for that, what we find is that the blood of the Shroud of Turin has only been decaying for 690 years when it was tested in 1998. When we say a source is highly radioactive, what we are really referring to is its activity, or rate of decay. The higher the rate of decay, the more radiation that is being produced, and therefore the more dangerous the sample. So decay rate really just says how many particles are decaying in a certain amount of time. Since the particles do not all decay at the same time, the decay rate really depends on the number of particles that are left to decay. When we say that the rate is proportional to the number that are left, we can write this as a rate of decay equal to some constant times the number of available nuclei. If you remember, we actually have a constant. So the rate of decay is equal to the decay constant times the number of particles that want to decay. Looking at this equation, we can see that if the rate of decay is high, then the decay constant has a large value. If the decay constant is smaller, then the rate of decay will be slower. Another way to look at it is to say that the rate of decay depends on how big the sample is as represented by n, and what fraction are going to decay at a time represented by lambda. So rate of decay is proportional to the number of radioactive nuclei, n, and inversely proportional to the half-life. It can be shown that when the rate of decay is equal to 0.693 times the number of radioactive particles divided by the half-life. The rate of decay is given in units of becquerels, in honor of the man who actually discovered radioactivity. 1 becquerel is equal to 1 decay per second. Now you might be thinking that in order for this number to represent 1 decay per second, that must be an extremely small unit. And you would be correct. Oftentimes we must express the decay in megabecquerels. And at times, another unit, called the Curie, is used. This is named in honor of Marie Curie and is actually the decay rate of 1 gram of radium-226, and it is equal to 3.70 times 10 to the 10th becquerels. So we can calculate the activity of a sample, say 1 kilogram of carbon-14. We know that the rate of decay is 0.693 times the number of parent nuclei divided by the half-life. We know the half-life of carbon-14 is 5,730 years, so we can plug that into our equation. But what is this n? N represents the number of particles that we are starting with. And well, we know that we have 1 kilogram of carbon. So if only there were a way to convert mass to the number of particles. A while back we talked about a mole being a unit that describes a certain number of particles. 6.02 times 10 to the 23rd particles, actually. We also became aware that the molar mass, or the mass of 1 mole of an element, could be found on the periodic table. In the case of carbon, 1 mole of carbon has a mass of 12 grams. We can set up a nice series of conversions starting with 1 kilogram is actually 1,000 grams. There are 12 grams in 1 mole and 6.02 times 10 to the 23rd particles in each mole. This turns out to be 5.02 times 10 to the 25th particles of carbon in our beginning sample. This is the total number of carbon atoms, though, not just the carbon-14 atoms. Now remember that the ratio of carbon-14 to carbon-12 in any given sample is 1.3 trillion to 1. So one more conversion gives us 6.52 times 10 to the 13th particles of carbon-14. We can plug that back into our activity equation, do the math, and find that the activity of 1 kilogram of carbon-14 is 7.89 times 10 to the 9th decays per year. This really equates to 250 decays per second for every kilogram of carbon, or 250 becquerels. Now if we want to convert that to curies, we need to take that 250 decays per second and divide by 3.70 times 10 to the 10th becquerels per curie, and we end up with 6.76 times 10 to the negative 9th curies.